Welcome to Lecture 1.8. In this video, I'll be going over 3 NMR spectra that I've prepared, again just hand-drawn spectra with approximate values, that we can use to understand and how we can approach NMR spectra. For each one, I've hidden the answer, along with the correct assignments, behind a box, and we'll see if we're correct as we go. Now, feel free to pause the video and try to solve these yourself, or follow along, however you want to do this. Below this video, you will also see some attached practice problems to give a try at. Keep in mind that NMR is really a skill that's practiced. I think I've given you my best tips and tricks for how to approach it, but the more examples you see and the more time you practice the mindset of solving these structures, the better you'll be when it comes to your assignments and your tests. So without further ado, let's get started. This might end up being a longer video, so feel free to take it in piecemeal. Starting with a relatively straightforward one, although definitely a step up from our ethanol in the last video, we have a molecule here, C7H14O. Right? Now, if we were to try to draw all the constitutional isomers of this molecule, we'd have a lot to choose from. It'd be very difficult. Luckily, NMR is going to give us the exact chemical structure. First thing that we're going to do is calculate the DOU. 2 times 7, number of carbon, plus 2. Subtract the number of hydrogen and divide by 2, gives us a DOU of 1. That means we have either one ring or one double bond in the structure, right? If you're using a technique like IR in synergy with NMR, you might be able to get an idea of what that DOU is represented by from the IR spectra, but we're not even going to necessarily use that today. NMR will be enough to solve this structure. So now that we have the DOU, let's fill in the table. Chemical shifts are 2.6, 2.4, 1.2, 1.1, and 0.8. A quick panning of those values tells us that these are all quite low in ppm, right? We see some slightly elevated signals around 2.4, but we don't see anything too crazy. At this point, we've totally eliminated benzene as an idea. 1, because of the lack of high chemical shift signals, and 2, because of the DOU that isn't as high as 4. Good. Now we'll touch the integration. The integration values are 2, 2, 3, 1, and 6. Let's sum them up and make sure that we actually have the assumption, right, that idea that integration is equal to the number of hydrogens. We can't know that until we add them up together. 4, 7, 8, 14 total. And look at that, that's equal to our formula, which means that now that we've confirmed that, our molecule doesn't have overall symmetry, and the integration can be assumed to represent the true number of hydrogen. Next, looking at the multiplicity, I can see that we have a quartet of 4 peaks, right? Simple splitting, a doublet of 2 peaks, equal height, a triplet. Now here with signal D, I just indicated that there are 9 peaks, but sometimes you'll be given expansions that really zoom in on a peak, and you can count them yourself. 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. Now we can call those a no-net. You'll be given a list of these to memorize, and I highly recommend you do. Signal E, then, is another doublet. Now here, we don't have a singlet, so let's make sure we don't make a mistake converting these multiplicities to neighbors, and just remind ourselves that a singlet, which is the smallest number of peaks, corresponds with 0 neighbors, the smallest possible number of neighbors. With that in mind, multiplicity to neighbors is -1. So our quartet would have 3 neighbors, doublet 1 neighbor, triplet 2 neighbors, no net, which was 9 peaks, it's going to be 8 neighbors, and the doublet will be 1 neighbor. Great. All the information of these 5 different signals, right, much more complicated than the previous one, is now laid out for us in the table. Let's just rewrite that chemical formula, C7H14O. Maybe we can rewrite it a bit cleaner than that. Right? And the fact that we have 1 DOU. This is all the information we need to solve our structure. Now, which signals are our doorway signals? Well, here we have signal D, right? Oh, sorry, that's multiplicity, right? That's not a doorway signal. Our doorway signals are signal E, which has an integration of 6, and signal C. Let's start with E. Here we see an integration of 6, which means to us that we might have an isopropyl group, right? 6 hydrogens that are identical, and they're a doublet, right? Remember that an isopropyl group, by definition, has that hydrogen here, which we would expect then these signals of 6 integration to be a doublet. Awesome. So 6 integration doublet, these are signal E for now. And remember, we've implied that this hydrogen must exist. So if we're not sure what that is, we can move on, but let's see if we can find out from our table which signal it could be. Right? Looking at the signal, right, what do we know about this expected hydrogen? Well, it should have an integration of 1. Lucky for us, there's only one option there, right? And that's signal D. Signal D has an integration of 1, and so it's got to be that one. Excellent. So now that we figured out signal D, we could move on, but well, let's just move to signal D, now that we kind of know where it's located. One thing we know about signal D, other than its integration, is that it has a total of 8 neighbors. And as of right now, it only has 6. That means that whatever's connected here must have 2 neighbors. And this is the power of the doorway method, right? We keep moving across the molecule, and at this point, I mean, look how much of this molecule we've already solved, right? There were no assumptions up until this step. That's the beauty of starting with this 6 and 3 integration signal. So once again, we've implied the existence of these 2 hydrogens, right? Can we assign them with confidence? Let's see. So these 2 hydrogens, we would expect integrations of 2. I see signal A and B, right? They both have integrations of 2, right? So we can't really be confident based on that alone. Looking at their multiplicities, though, well, we can't be really confident there either, right? All we know about this signal is that it has at least 1 neighbor, and both of these signals fit that, right? So we're really not sure what this could be, right? We know that it can't be, C at this point, but we can say maybe it's A or B. We're not really sure, and at this point, that's where we want to stop, right? We don't want to make an assumption that it's A and then keep going, or make an assumption that it's B. That could lead us astray. We're still using this doorway method at this point to avoid making assumptions. So with that in mind, we have our first puzzle piece, our first fragment, if you will. Right? Now, at this point, I like to revisit my doorways and see if I have any doorway signals left to understand. And what I see here is signal C. Signal C has an integration of 3, so let's draw that out. An integration of 3 is always going to be a methyl group. So, since it's a methyl group, there's only one way to go. What else do we know about signal C? Right, well, again, we're kind of not really looking at chemical shift too much at the moment. We know that it has 2 neighbors. Those 2 neighbors must therefore be connected to this adjacent carbon. The doorway shifts once again. Here we see 2 hydrogens, right? And so we can ask, well, can we, with certainty, assign them? So once again, just like we did in that previous fragment, we have 2 hydrogens, but we know that they must have at least 3 neighbors. That's the difference here. And that's really informative, because wait a minute, if our options are A or B, right? Pause the video for a moment, if you haven't recognized this yet, and try to assess which one is it signal A or B that we're talking about here. Okay? The answer is it has to be signal A. And the reason for that is that it has at least 3 neighbors, right? A fits that rule, but B doesn't. Because of that, we can make a pretty, no assumptions here that that is A. And if that's A, well, that means that this one's got to be B. And just by using the doorway method for this larger complex molecule, we've worked our way all the way here to identify every single signal in the molecule, right? We have A, B, C, D, and E. Wow, right? The whole molecule isn't done yet, but this has been very effective. So now that we've dealt with our doorways and we've dealt with all the hydrogens, let's try to connect the rest of the pieces and finish up this NMR spectra. Right? Time to do some arithmetic. C7H14O. I've dealt with 1, 2, 3, 4, 5, 6 carbons. All of the hydrogens are handled. We still have an oxygen left over, though. That leaves us with C, O, and keep in mind that we haven't introduced a degree of unsaturation yet in either of these fragments. right? There's no double bonds or rings. So feel free at this point, if you haven't yet solved the structure, to pause the video, use these fragments as well as this remaining information to try to come up with the final structure. Right? The only way to introduce both a carbon and an oxygen and a DOU without introducing any more hydrogen, since we can't do that anymore, we've already assigned them all, is to introduce the carbonyl. Right? We can connect a carbonyl to two different things, and that's lucky for us because we have two different things to connect. Right? So on one side, and it doesn't really matter, we'll have an ethyl group representing signal C and signal A. And on the other side, we'll have this group. Right? We have signal B, D, and E. And look at that. C7H14O, 5 different signals on NMR, which looks pretty complicated, but we were able to narrow down the exact chemical structure of this molecule. Right? We'll see what's behind the box to see if we agree with that, and look at that. Excellent. So that's the first example. Let's take it up a notch and jump to this molecule. Right? Now we're dealing with a much bigger molecule, right? C13H18 and 2 oxygens. Well, we'll approach it the same way. Start with the DOU. Right? That's going to be 2 times 13 minus, or plus 2, minus 18, number of carbon, number of hydrogen. That's going to get us to 5 DOU. So with that in mind, let's copy over the information from the table. Chemical shifts, integrations. Right? Before we move on to multiplicity, remember that we have to sum up the integration and make sure it adds up to 18. Right? Then we can make that assumption that integration is equal to the total number of hydrogen. In this case, that assumption is held. Multiplicities, we see 2 different doublets. Notice that they're at pretty high chemical shift values. That's consistent with being connected to a benzene. And we see more than 4 DOU. So benzene is very likely in this molecule. Right? There's going to be 1 neighbor each. Then we have a quartet, a triplet, and a singlet with 3, 2, and 1 neighbor respectively, or 0 neighbors. So with that in mind, let me just clean up that 2. We can redraw C13, H18, O2, and get started. So remember that because of that previous information with DOU and those A and B signals, it's very likely that we have a benzene ring in our molecule, and we can consider that while we do our doorway method. So applying the doorway, I see 2 different doorway signals, signal D and signal E. Starting with signal E, a 9H integration singlet can be very confusing, but it's a good pattern to catch on that would be a tert-butyl group. It has to be 9 different hydrogens that are equivalent by the rotation among that carbon. Right? While it is very useful to immediately deal with 4 carbons and 9 hydrogens that way, the fact that this has no hydrogen, that E is a singlet, prevents us from going any further. So this is our first fragment. Right? We don't want to start looking at this chemical shift for signal E and start making assumptions about what's connected 2 bonds away. That can lead you astray very easily. Now let's start with signal D. Right? Signal D has an integration of 3, so a methyl group. It's got to be connected to one thing, and we know that signal D has 2 neighbors. We can draw them both on this side since there's only one way to go. The question is now, can we assign these 2 hydrogens to a specific signal without making any assumptions? Feel free to pause the video and try to solve that. The answer is we absolutely can. Looking at integration might be kind of scary since all 3 remaining signals have 2 integration. But keep in mind that we know these 2 hydrogens have at least 3 neighbors. We're not sure what's connected here. We don't know the exact number of neighbors, but we know that any number less than 3 would be incorrect. That eliminates A and B and leaves us only with C. So these 2 signals must be HC. With that in mind, we can take a look at HC, right, before we jump any further, and say, well, how many neighbors does HC have? and HC only has 3 neighbors. It already has them, which means there's no neighbors on this side, and that we have another fragment. Right? So remember, by using the doorway method, in this case, we haven't solved our full structure or anything, but we have these known pieces. Right? Instead of dealing with 13 carbons and 18 hydrogens, we have these big pieces. So let's take a look now, real quick, and do some arithmetic. We have dealt with 1, 2, 3, 4, 5, 6 carbons, as well as the benzene, so 12 carbons. We've dealt with all of the hydrogens except for these 4, so minus 14 hydrogens. And we haven't dealt with any of the oxygens yet. That leaves us with 1 carbon, 4 hydrogens, and 2 oxygens left, as well as 1 DOU remaining. This is the point where we're going to have to start thinking creatively. Right? This is kind of the hard part of NMR, really, is once you've gotten these pieces, trying to figure out how to connect things. So a key piece of evidence for solving the rest of this problem is that we have 2 signals, A and B. They're in this benzene region, and there is a total of 4 integration in that region. 2 signals with 2 integration. That means that this benzene has to be substituted in a specific way. Right? Let's take a look at what I mean by that. So we know that this benzene has 4 hydrogens on it. Let's say that we had 2 different groups here that had this relationship where they were 1 carbon in between them. This wouldn't work. And the reason for that is that it would lead to 4 unique and distinct signals, right? This signal is closer to this group. This signal is closer to this group. Now, if those 2 groups were the same, they could potentially be symmetrical. But despite that, this hydrogen would always be unique along with this one, right? We wouldn't see that pattern of 2 signals with 2 integration. What's much more likely is that we have a relationship like this. Even with 2 different groups, we would expect these 2 signals to be the same due to that overall symmetry that we see with benzene, and these 2 as well. Now, we can't label these as A or B yet, but considering this, what could I put on these 2 positions? Well, now we want to take a holistic approach, right? We have our pieces. Let's take a look at chemical shift. Not of A and B just yet, but of C, D, and E, right? Signal C is at this ppm of 2.4, right? That's pretty typical for something that's beside a carbonyl, which is something to consider, right? We still have a DOU and a carbon, so let's start making assumptions, right? It's good we have to make them at some point, but make sure you're paying attention to when you're making them. It's possible that there's a carbonyl connected to this benzene ring. Then that would be connected to this fragment, which would contain HC and HD. Cool. What did that leave us with? Well, it handled our last DOU, it handled a carbon, and it handled one of our oxygens. Right? We also handled our 4 hydrogens here, so all that's left is 1 oxygen. And a possibility for that, right, considering that the only fragment left is this terbutyl group, is that we could put the oxygen here and a terbutyl group like so. Right? That would give us signal D here, or sorry, signal E, representing that terbutyl group. So this seems like a good option, although there are some limitations with it. So let's take a look here, right? Signal C and D, we talked about them. They have chemical shifts that agree, right? Signal E, though, is at a pretty low chemical shift, despite being 2 carbons away from an oxygen. Now, that's not necessarily disqualifying. It's just a little bit weird. The other thing to consider is the chemical shift differences between signal A and B, as we haven't identified them yet, right? Another possibility is instead of connecting C and D like so, we could take that extra oxygen and just make an ester, right? This would connect C and D just the same, right? C being beside a carbonyl makes sense, right? And then the terbutyl group could just be connected directly. This, from to my opinion, agrees a little bit more with the chemical shifts, especially when you look at signal E, right? And honestly, both of those answers, if you get either the one previously or this one, right? If I remember correctly, this should be the one that I put here. Yep, there's the ester group, right? both of those answers would get you many marks, right? There's always going to be one correct answer, but by filling out a table, making the fragments, and getting a structure that's arguably applicable to this NMR table, you're going to get most of the marks, right? There's lots of part marks up for grabs if you demonstrate your ability in NMR. Let's take a look at these two signals, though. Pause the video and try to tell me which one of these signals do we expect to be A and B. That's the one thing we haven't done yet. The big difference here, right? They would both be doublets. That makes sense. But the chemical shifts. What's up with them? Well, the key idea here is that there's an oxygen that is directly connected to the ring. This is an electron donor group, right? This is going to make some resonance forms, right, where we actually give electron density here, shielding these hydrogens, the ones that are adjacent to the group, right? Remember that donor groups donate electrons to those positions, here, here, and here, right, which we'll define more deeply in the next topic. But shielding, right, those electrons are going to shield. They're going to lead to a lower ppm. Now, they are closer to the oxygen, but we may actually expect HB, or rather, the orange hydrogens here, to be the more de-shielded signal, despite their distance. Considering that, right, let's move on to our last problem. All right, C9H18O3. We'll get right to the chase. We'll calculate our DOU as 2 times 9 plus 2 minus 18 divided by 2. That is going to be a DOU of 18 plus 2, so 21. 1 DOU. Okay, so 1 double bond, 1 ring somewhere. Only 3 signals, which is pretty surprising for a chemical that large. So the chemical shifts are 6.2, pretty high and elevated, 3.4, and 1.5. The integrations are 2, 1, and 6. And at this point, we once again want to check for the sum. And we'll notice, wait a minute, these only add up to 9. There's 18 total hydrogens, which means we need to double them to get values that agree with our total structure. Remember that when you do this, that is an evidence of symmetry in the molecule, which is going to be imperative in helping us solve this structure. The multiplicities are singlet, 1, 2, 3, 4, 5, 6, 7. 7 peaks is a septet, and a doublet for 0 neighbors, 6 neighbors, and 1 neighbor respectively. With that in mind, we have C9H18O3, and we can finish this spectra. So, applying the doorway method here, keeping in mind the idea that we probably have symmetry, let's just use these half numbers and try to solve half of the structure. Our only doorway signal here then would be signal C, and 6 integration with a doublet. That's the pattern we want to pick up on as the isopropyl group. So these hydrogens then could be signal C, right? And remember, the idea would be that somewhere else on the other side of the molecule, we would have another isopropyl group. For now, I'll just leave that empty. So signal C, right? We implied that there has to be a hydrogen here. Can we assign it? Yes, we can. Oh, I, for some reason, didn't double this. There's 2 there. Okay, so this would be signal B, the only signal that has 1 integration, or 2 if we had another group on this side. How many neighbors does HB have? It has 6, which means that it already has all of its neighbors from that isopropyl group, and whatever's connected here has no neighbors. Right? This would be our first puzzle piece, our first fragment. Awesome. So at this point, we're done with the doorway, right? We have 2 isopropyl groups. Let's take a look at what we have, right? So one thing to consider now is the chemical shift of signal B, right? 3.4, that's pretty textbook for being beside an oxygen, right? If we take a look at our quick math here, 2 isopropyl groups is going to be 6 carbons, right? That's 1, 2, 3, 4, 5, 6, 7, 14, if we double it, hydrogens. And we haven't dealt with any oxygens yet, meaning we have 3 carbons, 4 hydrogens, and 3 oxygens left to deal with. Don't forget, we still have that DOU as well. So let's make an assumption, right? let's take our fragment here, and based on that chemical shift, see what happens if we try to put oxygens there. At this point, I'll start drawing the other side of this molecule. Right? And notice how knowing that you have symmetry is a very powerful thing for this kind of spectrum. Right? Otherwise, there's a lot more difficult thinking, and we were able to catch that symmetry by recognizing that we doubled the integrations. So now, this idea that we have these oxygens, that handles 2 of these, meaning we only have 1 left. We have 1 DOU, 1 oxygen, 4 hydrogens. Let's investigate the one signal we haven't looked at yet, which is signal A. Right? 2 integration multiplied by 2 making 4 implies to us that we probably have what we call methine groups, or CH2s, 2 of them. Right? But notice this very elevated chemical shift. Right? We don't have a benzene or alkenes in this molecule, right? It's very difficult for us to interpret that chemical shift. But one thing to think about is, well, that DOU, maybe that's a carbonyl. That would deal with our last oxygen, and it would deal with a carbon. Right? Carbonyls can be connected to 2 things. That leaves us with, right? Oh, 1 carbon, so we have 2 left. 2 carbons and 4 hydrogens make sense with the idea that there are 2 different methine groups, or CH2s. So take a second, feel free to pause the video, try to take these pieces that we've put together, and solve the chemical structure. Right? The best way to do this would be to take your CH2 groups and connect them with a carbonyl. These CH2 groups would then be represented by signal A. And when we take a look at this, remember, we can always look back at our table and verify. Is the integration going to be 4 total? Absolutely. Will there be 0 neighbors for signal A? Yep, remember that oxygens prevent splitting information, and so we're not going to see A couple with B. So that all makes sense. But what about that highly elevated chemical shift? Well, remember, these are signals that are both deshielded by the direct oxygen and the adjacent carbonyl. Right? That's true for both of the signals. While we might not necessarily need to know the exact chemical shift of that signal, we should understand that it's going to be higher than we expect for just being beside an oxygen or a carbonyl, respectively. Right? The key idea with this question, is the idea of how we can use symmetry. And remember that if you saw this chemical shift and assumed that it was something like a benzene, you may have spent an hour on the spectrum instead of the 5 minutes that we spent. Verifying our complete structure, there it is, exactly what we thought. And that is how we can use NMR to find structural information. With that, I wish you the best of luck on the practice problems attached, and I implore you to do more practice in whatever resources your professor has given you. Right? With NMR, practice really makes perfect, but hopefully I've given you a good set of tools to make that practice more efficient.